This video will go through a series of 5 multi-step thermodynamic problems for students to work on. Please do these problems first, and then you can skip ahead to the appropriate video to go through the solution. Shortly, I will go through question number 1. The first question in this video asks to determine the amount of energy released when 1 kilogram of carbon completely combusts. In order to solve for the amount of energy released, we're going to need to know the moles of chemical released, which we can get from the mass, and we're going to need to know the molar enthalpy that corresponds to that same chemical or carbon that we know the mass and ultimately the moles of. There is no energy data given in this question. Whenever you have a question where there's no calorimetry data or the energy released for a certain mass is not given, you're going to have to use your formation data table to predict the enthalpy change for the balanced chemical equation and the molar enthalpy, which is ultimately what we want. So this is the combustion of carbon. Carbon elementally comes in ones. Combustion is any reaction that involves oxygen as the other reactant. Okay? This is a combustion reaction, but it is not a hydrocarbon combustion. So we do not get CO2 and water. The only product we get is carbon dioxide from this combustion. Okay? Now this reaction is balanced as written. There are no stoichiometric coefficients other than ones required. Okay? And I want to know what the enthalpy change of this reaction is and ultimately the molar enthalpy. Okay? Now when I look up the change in molar enthalpies of formation in my data booklet, the 2 reactants aren't listed because atoms in their elemental form have formation values of 0, and the formation value for gaseous carbon dioxide is minus 393.5 kilojoules per mole. Okay. Because there's only 1 mole of carbon dioxide in this reaction, the enthalpy change for this reaction will be minus 393.5 kilojoules for that 1 mole. Okay. Okay. Now ultimately what we're going to want is the molar enthalpy of reaction of carbon dioxide, which, because this is a formation reaction, is the value we looked up. Okay. So this is the key value that we had to look up. We know the energy released per mole, and now we just need to figure out how many moles we're going to have released, not in this balanced chemical equation, but when 1 kilogram is released. So the enthalpy change for our 1 kilogram of pure carbon reacting is going to be the moles of carbon times the molar enthalpy of carbon. Okay. To emphasize that, I'm just going to put a little subscript C, so that is moles of carbon, and this is the molar enthalpy of carbon. Okay. I'm going to solve for my moles right in the balanced chemical equation. That carbon is a pure substance. It is not a solution, so we can use mass over molar mass. So we have 1.0 kilograms, which would be 1,000 grams, okay, divided by 1 mole of carbon. The molar mass for 1 mole, the mass for 1 mole of carbon. So that will give us our moles times our molar enthalpy for carbon. The value we had to determine from our data booklet. We'll ultimately have grams cancel grams. That moles is on the bottom of the bottom, which is the equivalent to being a numerator, and that will cancel with our denominator moles. So we're left with just kilograms. That minus sign is going to go to the front, so we're going to have energy released. And our kilograms, our 1.0 was to 2 significant figures, so I'm going to record my answer to 2 significant figures. So we have 33 kilojoules of energy released in the combustion of 1 kilogram of carbon dioxide. Moving on to the next example from my class's student workbook that I want to go through is question number 3. In this question, you're asked for the enthalpy change for the given reaction, and you're given some information to use to help figure that out. Okay. Ultimately, if we know the molar enthalpy of any of those 4 chemicals, either the sodium reactant, the phosphoric acid, the hydrogen gas, or the sodium phosphate, we're going to be able to figure out the enthalpy change of this reaction. Okay? And we have data for hydrogen. Okay? We have enough information given in the word part of this problem to solve for the molar enthalpy for hydrogen gas. Okay? Once we figured this out, because this equation has 3 moles of hydrogen in it, we can just triple that molar enthalpy or multiply it by 3 moles and get the enthalpy for this particular reaction. So molar enthalpy can be calculated if you have the change in enthalpy for a corresponding amount of moles. Okay? The key is they have to link together. Okay? So we have 30 kilojoules of energy released, and we have to get the moles that caused this release. Okay? It is not any of the moles in our balanced chemical equation. It is that 1.01 grams of hydrogen that caused that energy release. So I'm going to link those 2 variables together to figure out molar enthalpy. Okay. The energy change, or the enthalpy change, I don't have to do any calculations. That's 30.0 kilojoules. Now it is energy release, so I need to remember to put my minus sign in for an exothermic reaction. Okay. I need to figure out the moles of hydrogen on the bottom. Okay. Our moles of hydrogen gas, mass over molar mass. That is not a solution, it's a pure substance. 1.01 grams of hydrogen divided by the molar mass, which is 2.02 grams per mole for diatomic hydrogen. So this works out to be half a mole. So we have 30 kilojoules released for half a mole, or expressing it as a molar enthalpy, we're going to have 60 kilojoules released per mole. Okay. Okay. Now to solve this question, I'm going to do it orally first, or just thinking our way through it, and then I'll do it with a calculation. Okay. 60 kilojoules is released for every mole. Okay. I want to relate this now to our equation. I'm letting go of the 30 kilojoules and the 1.01 grams. Our equation has 3 moles of hydrogen in it. Every one of those moles is going to release 60 kilojoules. So the first one would be 60, 2 of them would be 120, all 3 of them would be 180 kilojoules released. So the enthalpy change for this reaction is going to be 180 kilojoules. Okay? And that is the energy released for the whole equation. Okay, for this recipe, when 6 sodium and 2 phosphoric acid units and 3 hydrogen units are created and 2 sodium phosphate units, that's the energy released. Okay. So I did that without a formula. Using a formula, the enthalpy change for our equation, okay, I'm going to determine by moles and a corresponding molar enthalpy. Okay. Now we have this data for hydrogen, so moles of hydrogen molar enthalpy of hydrogen. It's key that those are the same chemical and the same circumstance. So we have 3 moles in the balanced chemical equation. Molar enthalpy is true for any situation, whether it's any type of real life reaction. So that is 60 kilojoules per mole. Okay. And that will output 180 kilojoules. Okay. Again, because the moles came from the equation, the delta H is true for the equation as written. So that's how you can calculate the change in enthalpy for the reaction in this question. I'm now going to solve the 3rd question in this video series. It's number 5 from the multi-step questions in the workbook that my students have. And before I solve this, I want to give a bit of a picture, a graphical interpretation to help solve this. Okay? So we're asked what mass of octane must be burned to heat some ethylene glycol from a certain initial to final temperature. Okay? So this is very much like a combustion experiment that you may have done in class. So for the burning of the octane, I'm just going to put a little burner. Here's your octane. And there is some container of ethylene glycol coolant. Now, in this question, we can determine exactly how much that coolant, how much heat that coolant has absorbed. Okay. We're given specific heat capacity, temperatures, the mass of coolant, so we can know the Q, okay, or the enthalpy change of this coolant. Okay. That can be solved for. Okay. In terms of our fuel, okay, we're going to need to know how much of that fuel needs to be combusted to give that exact same amount of energy that went into the coolant. Okay? If the coolant gained 1,000 kilojoules, it must have come from the combustion of and the release of 1,000 kilojoules down below. Okay? So we're going to need to know the moles and the molar enthalpy of our fuel in order to figure out how much energy must be released. Okay? And ultimately, we're going to solve for not the moles, but the mass of octane. Okay? Now, we don't have any data in this question that lets us solve for molar enthalpy. So we're going to have to use the common technique of a balanced chemical equation, use the formation values, get the delta H for the reaction, and then figure out the molar enthalpy. Okay? It's a lot of work, and it's just to get the molar enthalpy for the chemical that we're interested in. Okay? So let's start with a balanced chemical equation. So we have octane, okay? Oct meaning 8, so C8H18. That is going to undergo a combustion reaction, so react with oxygen to create carbon dioxide and water vapor. Okay, this is open combustion, so that's how I know it's water vapor. And I'm going to want to solve or predict the change in enthalpy using our data booklet. Okay? And ultimately use that to get the molar enthalpy of our fuel. Okay. Well, I need my equation to be balanced before I can make that prediction. So we have 2 units, 25 units, 16 units, and 18 units of water vapor. So I'll predict the change in enthalpy under standard conditions, because our data booklet only gives us standard conditions, by summing up the moles times the molar enthalpy of formation of all our products and subtract that from our reactants. So I always like to open a bracket, do the first sum, close it, do the hit right subtract, and then I'll open a bracket for our reactants. So we have 16 moles of carbon dioxide minus 393.5 kilojoules per mole. Okay. First product, now I'm doing my sum plus my second product, 18 moles of water, and make sure you get water vapor from your data booklet, minus 241.8 kilojoules per mole. I've completed my two products, so I'm going to close my bracket, put in my subtract, products done, subtract, I'm into my sum of my reactants, 2 moles times the molar enthalpy of my octane, minus 250.1 kilojoules per mole, plus OC25 oxygen, the formation, molar enthalpy of formation of any atom in its elemental form is going to be 0, so I'm not going to write out 0 times the 25 moles. When you put everything into your calculator, if you have a graphing one, you can put one in exactly as I've written it out, obviously without the units, but with the brackets as I have them, and you should get a release of 10,148.2 kilojoules. Okay. So that's the enthalpy change of our reaction, and we're doing all of this work so that we can get the molar enthalpy of our fuel, C8H18. Okay. Okay. To do that, we have to have a corresponding enthalpy change in moles, and our balanced chemical equation with an enthalpy change gives us this. Okay. That 10,148.2 kilojoules was released for every 2 moles of octane. So that gives us the molar enthalpy we've been looking for, 5,074.1 kilojoules per mole is our molar enthalpy. Okay. All of that just to get that blue circle, that molar enthalpy of our fuel. The moles of our fuel, where the blue arrow is pointing, will be the last thing we'll solve for. We need to figure out how much heat was absorbed by that coolant. Okay. And then we can put everything together and solve for the moles. Okay. So I'm just going to put a line to sort of wrap up that part, and I want to know the delta H, or we're going to do this by getting the Q of the coolant. Okay. Q is heat, delta H is enthalpy change. They both have the same number. Q is the transfer of heat. Enthalpy change is a vector. It has both the direction and the numerical value. So our coolant, Q, is mass of the coolant times specific heat of the coolant times the temperature change of our coolant. So we had 20 kilograms, or 20,000 grams of our coolant times the specific heat capacity. Now, this is not a chemical given in your data booklet, so it is given in the question. A little less than water, 3.7 joules per gram per degree Celsius, and we need the temperature change of our coolant. So it started at minus 10 and went up to 70. So that is a difference of 80 degrees Celsius. So that gives us a amount of energy or heat that went into our coolant First, I'm going to write this in joules. Okay. Or I'm going to convert this to kilojoules, and it's 5,920 kilojoules when I divide my joules by 1,000. Okay. So we now know how much energy went into the coolant. Okay. We know how much energy per mole the chemical we burnt can produce. So now we have all the pieces we need to solve for how many moles of coolant are needed. Okay. So we're totally diving into this diagram now. Okay. This Q is known. Okay. We know our molar enthalpy, and we're going to solve for that moles. Okay, this diagram is the circumstance that I'm about to be solving for, okay, not the balanced chemical equation. Okay, so the change in enthalpy, okay, this is of the coolant. Okay, this is really coming from Q, okay, is going to be equal to the N times molar enthalpy, okay? And this is coming from our fuel, okay? And we're assuming 100% efficiency, that all the energy produced by the fuel, the moles times the molar enthalpy, is going to go into the coolant. Okay, so our Q was 5,920 kilojoules, okay? That was energy released, so I'm just going to add that minus in for our delta H, which is a vector, which shows the direction. Okay. N, we don't know. That's what we want to find out. Our moles of our octane and our molar enthalpy of our octane, 5,074.1 kilojoules per mole. Okay. So we can rearrange this and solve for our moles. Minus 5,920 kilojoules divided by our molar enthalpy. Okay, this is why we converted our Q before from joules to kilojoules, so that they would later cancel out with our molar enthalpy, which was in kilojoules. We have moles on the bottom of the bottom. So that's equivalent to moles to the -1 to the -1, which is just moles. Which is 1.167 moles. I know I have some extra digits, but we're not at the answer, so I'm not rounding down yet. Okay. Last, we've completed all the thermodynamics. Now it's just figuring out what mass that is. You can get mass of any chemical if you take the moles of that chemical multiplied by the molar mass. So that's our moles of octane times the molar mass. And we will have our grams, 133.3 grams. Now looking in this question, there's only 2 significant figures given in most of the data, so propagating through, I'm going to report my final answer to 2 sig figs. I'm going to choose to use kilograms. I'm going to divide that answer by 1,000, and then I have no worry about zeros that may or may not be significant. So 130 grams or 0.13 kilograms is the mass that must be burned to warm that coolant. The next question that I'm going through in this series of examples is very similar to the previous one if you watched that video. We have a fuel being burnt, the heat is going into some substance, and we're asked this time not how much fuel had to be burned, but how much carbon dioxide would be produced when that ethane fuel has been burned. So I'm going to start with pretty much the same diagram as I did before. We have some burner, fuel. This is my lovely fire. We've got ethane burning, and we've got the heat going into something. We don't know what it is. We can't do Q is MC delta T. We don't need to do it because we know that the amount of heat that went into this is 1,500 kilojoules. Okay? So this question is a little simpler. We know that heat. Okay, we need to figure out how much not fuel was burnt, but how much CO2 was produced in this combustion. Okay? So we're going to ultimately need, what we care about down below is carbon dioxide. Okay? So we're going to need to know, solve for the moles and the mass, and we're going to need the molar enthalpy, but not of the fuel this time. We're going to need the molar enthalpy of carbon dioxide that was produced. Okay? We'll know how much energy is released per CO2 produced, and we'll figure out how many moles are needed in order to get that 1,500 kilojoules. Okay? Similar to the previous question, we have no data given in this question to get the molar enthalpy of carbon dioxide. So I'm going to write a balanced chemical equation, use formation values to predict its enthalpy, and then get the molar enthalpy, okay, of the product we care about. So we have, what is our fuel? Our fuel is ethane, C2H6. I'm using the generic formula. All anes are 2N plus 2s. Okay. That is a gas, reacts with oxygen gas. Okay, this is just a complete combustion, produces CO2, gas, and water vapor. Okay, I want to know the enthalpy change, and really, I want to know the molar enthalpy. Okay, I need my equation balanced so that I can do the sum of the moles times the molar formation of all the products minus moles times the molar enthalpy of formation of all the reactants. So I'm going to start with my 4 CO2. I even like to sometimes check them off as I work my way through them. So we have exactly 4 moles times the molar enthalpy of carbon dioxide. This is the sum part plus my 6 water vapor. Making sure again you grab the correct water value from the table, the gaseous one. Okay. That concludes my products. I'll close the bracket. I don't quite have enough room to keep going across, so I'm just going to continue subtraction and move into my reactants down below. I have 2 ethane. Again, all these molar enthalpy values are looked up in your Chem 30 data booklet. Next, I'm on to a elemental form, so that's going to be 0. And sometimes you'll see solutions written where it's not even written out. So I'm going to do that just so you can see the plus 0 was totally omitted. So that gives us a change in enthalpy of minus 2,856.8 kilojoules, and lets me solve for what I really want. The whole point of this is getting the molar enthalpy for the chemical in question. which is carbon dioxide. Okay, I want to know how much energy is released per mole of CO2 production. Okay, so I'm going to use my balanced chemical equation. I'm going to get the delta H from the equation, and I'm going to get the corresponding moles from the equation. Okay. Nothing to do with this blue calculation, has to do with my black diagram. This is all coming from the equation. So that's the kilojoules from the equation. Carbon dioxide, how many moles caused that? 4 moles were produced to get this amount of energy. And that 4 is not one significant figure. It is perfectly exactly 4 infinite sig figs. Okay. So all this work just to get the molar enthalpy. Okay. Every mole of CO2 produced, we're going to get 700-ish kilojoules. Okay. So now I'm ready to really tackle the question. Okay. I know the heat that's produced. I know the molar enthalpy of the chemical that's going to produce that heat. And so I can now solve for, I'm not going to check that off yet, I can now solve for the amount of moles that must be needed, or in this case produced, to get that 1500 kilojoules. Okay. So the change in enthalpy, okay, of that created this Q, okay, it's going to equal the moles times the molar enthalpy of the chemical that was created in the combustion. So we have 1500 kilojoules that was released, okay, and that's released, so that's minus equals our moles times molar enthalpy. So I give a reminder that everything on this side is for CO2, both the moles and the molar enthalpy. So our moles we're going to get from rearranging and isolating for N. And that works out to about a little over 2 moles of carbon dioxide was produced. Okay. That's pretty much it for our thermodynamics. Now it's back to Science 10 or Chem 20 mass calculation. You know, what mass was created or is equivalent to that many moles. So mass is moles times molar mass. So the mass is our 2.10 moles multiplied by the mass of 1 carbon and 2 oxygen. So that is the mass of 2 carbons plus 1 oxygen. And we get 92.4 grams of CO2 had to be produced to get that 1500 kilojoules. This would be a pretty typical test question, and it is something that should be doable with lots of practice in the 3 to max 5 minute time frame. I'm now going to solve the last question in this series of 5 examples from my class's Chem 30 workbook. Very similar type of initial situation, except for it's a bomb calorimeter. All the setup is going to be the same, except for in bomb calorimetry, you have the combustion of the reaction occurring right inside the calorimeter. Okay? Now in a bomb calorimeter, you're going to have some thick-walled calorimeter that can literally handle an explosion. It is a a bomb if it ever broke. Okay? And the chemical reaction is going to occur inside this metal vessel. Okay? Now this metal vessel, which is my black box or black metal around, might be surrounded by water also. Okay? And to solve for the amount of heat that goes into this bomb calorimeter, your Q equals not little mc delta T, but big C for this bomb calorimeter times the change in temperature of that calorimeter. So actually a simpler calculation than the mc delta T. Okay? Now the reaction is going to occur inside this calorimeter, and the energy from the reaction, same as before, is moles times a corresponding molar enthalpy. Will tell us that energy released by the chemicals. The Q is big C delta T, will tell us the energy absorbed by the surroundings. Okay? So we're going to tackle this question, very similar to all the others. Okay? What do we know? Where are we going to start? Well, we're told the mass of methanol, so we can solve for the moles quite quickly, and we're going to have to do what we've done in most of the questions. We're going to have to write a balanced chemical equation, solve for the enthalpy, and then get the molar enthalpy for the chemical we care about. Okay? So we're going to start with moles times molar enthalpy in the first half of this solution. Okay? Once we solve for those, we'll know how much energy was released by the chemicals, and that will ultimately tell us our Q value. Okay? The C value is given in our question, and so finally at the end we can tackle what is the change in temperature for this surrounding. So I'm going to get started with the balanced chemical equation, delta H, molar enthalpy. So we have methanol that's reacting or combusting in this calorimeter. So meth is one carbon with an OH. It's going to react with oxygen gas. It's going to produce CO2 gas. And one difference, we're going to get water like we do in combustion, but it's going to be liquid water inside a bomb calorimeter. This is not an open system like you would have burning something open on a lab bench. Okay? So we're going to have to watch out and make sure we look up the correct water value in our table. Okay? Most of the time you're looking up water vapor. Okay? Now the molar enthalpy that we're going to want is for our methanol. But we got to get the delta H first. We need a balanced chemical equation. Okay. Solve for our delta H. Okay. I'm going to skip writing out sum of moles times molar enthalpy of the products minus the reactants and jump right into that calculation. So we start with a bracket and check off my chemicals as I do them. So 2 moles of CO2. Done my first reactant, and now I'm going to do the sum. I'm going to add the next product. 4 moles of water times water liquid has a higher formation enthalpy change, okay, higher in magnitude. Okay, so I'm not talking about the sign, more energy released. Okay, that's the end of my product. So I'm going to move to my reactants. I'm going to continue this down below, minus, move on to reactants. First one is our methanol. 2 moles times formation of methanol, molar enthalpy formation of methanol. Okay. And move on to my last reactant. That is a elemental form, so I'm not going to write the +0. So that gives us a change in enthalpy for our balanced chemical equation. of 1,451.8 kilojoules. And the whole point of doing all of this is to get a molar enthalpy for this reaction, which is a combustion, for the chemical we're told we have to use. So that is methanol. We have 3.41 grams of methanol, so that's the molar enthalpy that I want. So I'm going to take the delta H from the equation and the moles from the equation. And these are variables. You have to use corresponding values whenever you're using the equation that I'm using. So that's the energy released for the whole equation as written, and the methanol has 2 moles. So we finally have our molar enthalpy. Okay. All of that work just to get one small piece. Okay. We now actually know that red arrow, that red check mark, that molar enthalpy. Okay. The moles we can get quickly, so we're going to know the amount of energy released in this bomb calorimetry reaction. Okay. Everything so far in blue is for the equation. Let's move on to this bomb experiment. Okay. This bomb experiment is when there's 6.40 grams reacting. Okay. I want to know how much energy is released when that 3.4 grams reacts. Well, moles we can get from mass over molar mass, so 3.40 grams of methanol reacted. Okay. I'm doing all of this for methanol. Okay. Moles of methanol, molar enthalpy, which is always true, and that will output the delta H for our 3.4 grams of methanol. Okay, so that will give us our moles times our molar enthalpy. And we're going to solve for how much energy was created by the chemicals and how much must have gone into the surroundings. This is a release of 77.01 kilojoules. So I'll just pop, we're almost ready to finish this, but just connecting this to our diagram. Okay. So we're now saying that the chemicals spit out approximately 77 kilojoules. Okay. Where did that heat go? It went into our bomb calorimeter. Okay. So our Q, the heat that went to our calorimeter is going to be 77 kilojoules. Okay, we know it's into the calorimeter and it's going to drive the temperature up because of the fact it's negative 77. Okay, so we know our Q, the C is given right in the question. We can solve for the change in temperature or the increase in temperature in our bomb calorimeter. Delta T. So Q is big C delta T for a bomb calorimeter. This wasn't a bomb calorimeter, would just have an MC delta T, very similar. Okay, our Q, we normally convert the Q to joules, but in the question, the C value is given in kilojoules. says kilojoules per degree Celsius. So I don't want to convert to joules for my Q like I normally do. I'm going to leave it. So we have 77.01 kilojoules of heat. Okay. I'm not putting the minus in because now I'm leaving the vector and going to the scalar Q. Okay. Equals C, that is 6.75 kilojoules per degree Celsius. Okay, so that tells us how much energy is needed to heat that calorimeter, 1 degree Celsius, times our delta T. So our delta T equals kilojoules cancel. We have degrees Celsius to the -1 to the -1, which is, or of the bottom, which is just degrees Celsius, and we get 11.4 is our change. Okay. And again, just highlighting because energy was released by our chemicals, this is an increase in temperature. So that concludes this series of 5 video worked solutions.